In Chapter 4, we're going to look at probability, random variables, and probability distributions. But in Section 1, we're going to go ahead and start with some basic probability rules. So one of the most important things that has to go with probability is randomness. So rock, paper, scissors, coin tosses, lottery and casinos, games involving dice, spinners, or cards, so on and so forth. So those are kinds of things that have randomness in it that we can find probability. Even traits we inherit, gender, hair and eye color, blood type, dimples, they're all determined by the chance involved in which genes get passed along. So all of these represent chance behavior. And we can understand and work with this chance behavior using basic probability rules. So all of these outcomes are governed by chance, but in many repetitions, a pattern emerges. So like I can flip a coin 2 times in a row and get heads. It doesn't change the probability of getting heads. But if I were to flip a coin 200 times, I can see a pattern emerging about the number of heads and tails I get. So we use mathematics to understand the regular patterns of chance behavior, and that's what's called probability. So probability is chance behavior that is unpredictable in the short run, but has a regular and predictable pattern in the long run. So that goes back to my example with the flipping coin. There are 2 probability types: empirical probability and theoretical probability. So the first one is empirical probability. Okay, which is based on actual observations. So if I flip a coin 500 times and I get heads 489 times, the empirical probability is 489 out of 500. Is that likely? No, but that's empirical probability. Theoretical probability is empirical probability based on an infinite number of trials. So we expect that out of an infinite number of flips, half of coins, half of them should land on heads. So the theoretical probability is 0.5. So empirical is what you actually get when you perform an experiment. Theoretical is what you expect to happen. So some probability terms that we are going to be seeing a lot of. So the first one is random event. So a random event is an activity with a measurable result. So like flipping a coin. My random event can be flipping a coin. There is a measurable result in flipping a coin. The outcome is the result of one trial or of one random event. So if I flip a coin once, and whatever I get is the outcome. So my random event, flipping a coin, flipping it once is my one trial. The event is a set of related outcomes. So like I can say my random event of flipping a coin, I can define my event as flipping a coin a number of times. And then we have our sample space, which is the set of all possible Usually we denote this S equals, and then we use curvy brackets to kind of contain our possible outcomes. So like for flipping a coin, my sample space is heads and tails. Those are the only two outcomes I can get when flipping a coin. So sample space can be as small as 2 outcomes. It can be as large as 52, which is something we'll talk about a little bit later. So first thing we're going to talk about is our simple probability formula. So the probability of an event is the, in general, number of outcomes in the event divided by the number of outcomes in the sample space. So we say the probability of some event E equals, and then our numerator is our number of outcomes, and then our denominator is our sample space. In this formula, all of the outcomes in our sample space must be equally likely. So there can't be a chance that, like flipping a coin, it can't be like a weighted coin where heads is more likely to happen than tails. They all have to have an equal chance of happening. So let's look at some examples. We have a bag that contains 10 marbles. 2 of them are black, 3 blue, 1 red, and 4 white. We want to find our probabilities. So the first one, probability of pulling out a black marble. So number of outcomes. So how many of my marbles are black? 2 out of my sample space, which I know is 10 marbles. So 2/10, which we want to simplify as often as possible, which is 1/5. What about the probability of pulling out a red marble? So there is 1 red marble in my entire bag of 10. So that's as easy as the simple probability formula gets. Next, let's look at an example with dice. So we rolled 2 dice and the sum of the pips is noted. So the little dots on a dice are called pips. We want to find the probability that a sum of 9 is rolled. So this one's a little bit different because we're looking at rolling 2 dice and getting a sum of 9. So if you think of if I have 2 dice, there are both labeled 1 through 6. I want to find the probability that I get a sum of 9. So how many ways are there to get a sum of 9 when I roll 2 dice? So in this case, my sample space contains 36 outcomes because I have 6 outcomes on my first die times 6 outcomes on my second. And so the combination of all of those possible outcomes makes up my sample space. So I can do a 1 and a 1, a 1 and a 2, a 1 and a 3, so on and so forth. Next, I want to figure out how many ways are there to add to 9. Well, I can do 3 and 6, but I can also do 6 and 3. So that counts as 2 outcomes because if the first die has a 3, but the second die has a 6, that's different than the first die being 6 and the second die being 3. The other way is doing 4 and 5 and 5 and 4. So there are 4 ways to get a sum of 9 when you roll 2 dice. So I get 4 out of 36, which simplifies to 1/9. Let's go to an example of flipping a coin. So we flip a coin 3 times. And we record the results of each flip. I want to find the probability that exactly one of the flips results in heads. So this time I'm going to actually write out my sample space here. So I can flip heads 3 times in a row. I could flip tails 3 times in a row. I could get heads on my first flip, then tails twice. I could get heads twice and then tails. I could get tails, heads, tails, tails, heads, heads. I could get heads, tails, heads. I could also get tails, tails, heads. So these are all of the possible outcomes when flipping 3 coins. There are actually 8 outcomes. So I want to find the probability of getting 1 heads out of my 3 flips. So I have 8 outcomes. I want to know how many of them resulted in exactly one of them being heads. So we have heads, tails, tails, and we have tails, head, tails, and we have tails, tails, head. So that means 3 of my outcomes resulted in exactly one of them being heads. My next probability is what's the probability that at least one of the flips resulted in heads. So that means 1 or more heads. So out of my 8 outcomes, the only time I didn't get heads at least once was when I have 3 tails. Every other time, heads appeared at least once. So only 1 out of the 8 results, 7 out of the 8 results had at least 1 heads appearing, because only 1 of them didn't. So when we're talking about the definition of probability, we talked about what probability is, but there's a couple of things that go along with calculating probability. So the probability of any outcome of a chance process is a number between 0 and 1. 0 meaning it will never happen, and 1 meaning it will always happen. You can kind of think of these as percentages as well, 0% or 100%. So it describes the proportion of times the outcome will occur in a very long series of repetitions. So the idea of probability seems very straightforward. It answers the question, what would happen if I did this many times? So for probability, randomness is only predictable in the long run. So that's what probability is. It's probability in the long run. It's not probability in the short run. Unfortunately, intuition about randomness tries to tell us that random phenomena should also be predictable in the short run, which leads us into what we're going to talk about next. There are 2 very common misconceptions or myths that have to do with probability. The first one being the myth of short run regularity. So the idea of probability is that randomness is predictable in the long run. So that would be 1 million plus occurrences. That's what we consider long run. Probability does not allow us to make short run predictions, which is a very common thing, that misconception. The other one is the myth of the law of averages. This is very, very common in sports. So probability tells us that random behavior evens out in the long run, but future outcomes are not affected by past behavior. So a lot of times in sports, you'll say, especially in baseball, they'll say he hasn't had a hit in the last 3 at-bats, but his batting average is very high. They'll say he's due a hit. Just because his past at-bats haven't resulted in a hit doesn't mean he's due a hit. Every time he goes up to bat, his batting average, that's his probability of getting a hit. So for another example of here is that women have a 50% chance of having a boy with each pregnancy. Just because maybe you've had 3 girls up until that point doesn't mean you're due a boy. Every time the probability is 50%. So the gender of any previous children does not matter. So let's talk about some basic probability rules. The first one being that the probability of any event is always a number between 0 and 1. Probability of an event is the long-run proportion of repetitions on which the event occurs. All possible outcomes together must have probabilities that add up to 1. So in your sample space, each event in your sample space is going to have a probability. If you add all of those probabilities together, you have to get 1. Since those are all of the possible outcomes, you have to end up with 1 when you add them together. The probability that an event does not occur is 1 minus the probability that the event does occur. Since the probability of something happening and not happening, if those are your only 2 outcomes, they have to add to 1. So you do 1 minus the probability it occurs, and that will give you the probability it does not occur. This is something called a complement. So when we refer to an event like not A or not happening, we denote it with, so if our event is A, it's A with an exponent of C. So the probability of A can be thought of as 1 minus the probability of not A. You can also think of the probability of not A equaling 1 minus the probability of A. And then lastly, the probability of A plus the probability of not A have to equal 1. So all of these are correct statements involving any one event A. A very common occurrence in probability is something called mutually exclusive. So it's specific to when you're looking at 2 events. So if 2 events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. When 2 events have no outcomes in common, we refer to them as mutually exclusive or disjoint events. So what that means is, if 2 events are mutually exclusive, the probability of A and B, so the probability of both happening, is 0. What that means is they cannot occur together. We're going to look at an example of how this works. So I have a very nice picture here of all of the possible outcomes of rolling 2 dice. So, and they are colored, like the first die is red, the second die is white. So you have your 36 outcomes here for rolling 2 dice. One of them is going to come up red and one of them is going to come up white. We want to know the probability of rolling a sum of 5 or 2 even numbers. So our first event A, we are going to let be sum of 5. Our second event B is going to be 2 even numbers. So I first have to decide, are these events mutually exclusive? So can I get a sum of 5 by adding 2 even numbers? So what I'm going to go through here, and I'm going to highlight all of the outcomes that have a sum of 5. So we think we can do 4 and 1, 3 and 2, 2 and 3, 1 and 4. So all of those are my outcomes of getting a sum of 5. Next, I'm going to highlight all of my 2 even numbers. So that's 2 and 2, 4 and 2, 6 and 2. And I have 2 and 4, 4 and 4, 6 and 4, and then 2 and 6, 4 and 6, 6 and 6. So if I look, none of them overlapped. I didn't highlight any boxes that were also a sum of 5, which means these events are mutually exclusive. So the probability of A or B, so that's what represents mutually exclusive. You're saying the probability of A or B is going to equal the sum of 5 here, which there were 4 out of 36 outcomes, plus my 2 even numbers, of which there were 9, which gives me 13 over 36, which does not simplify. So there are 13 out of 36 outcomes where you can get a sum of 5 or 2 even numbers. So that leaves us to our formula for general addition for two mutually exclusive events. So it says if you're trying to find the probability of A or B, so one or another event happening, all you do is add their probabilities. So probability of A plus the probability of B. So our second example, we have that online courses are rapidly gaining popularity among college students. Randomly select an undergraduate student who is taking an online course for credit and record the student's age. And here is our probability model. So we have 4 different age groups, 18 to 23, 24 to 29, 30 to 39, and 40 or over. And then we have the probability that they're in that age group. So if you want to show that something is a legitimate probability model, that's when you make sure that all of the probabilities add to 1. So we'll do 0.57 plus 0.17 plus 0.14 plus 0.12, which does equal 1. So it is a legitimate probability model. Part B asks us to find the probability that a chosen student is not in the traditional college age group, which is 18 to 23 years. So we're finding the probability of not 18 to 23. So we're finding the probability, if we denote this as my event A, I'm finding the probability of not A, which we know from our previous page I can do as 1 minus the probability of A, which means 1 minus 0.57, which is 0.43. Other option here is to add the ones that are not 18 to 23. So I can do 0.17 plus 0.14 plus 0.12, which also gives me 0.43. So both of those are valid methods to find the probability that you're not 18 to 23. For our last example, we'll go back to our dice. So we're rolling 2 fair 6-sided dice, 1 red and 1 white. We want to know the probability of rolling a sum of 6 or 2 even numbers. So I'm going to let event A be sum of 6 and B equal 2 even numbers. All right, to get a sum of 6, I'm going to go ahead and highlight my outcomes. I can do 5 and 1, 4 and 2, 3 and 3, 2 and 4, 1 and 5. Now for 2 even numbers. So we did that before. 2 and 2, 4 and 2, 6 and 2, 2 and 4, 4 and 4, 6 and 4, and 2 and 6, 4 and 6, and 6 and 6. So if you noticed, I actually highlighted over 2 boxes the same for both events. I had to highlight 4 and 2 and 2 and 4 because those are 2 even numbers that have a sum of 6. So when I find my probability here, I don't want to count those outcomes twice. So I have the probability of A or B. Okay. My sum of 6, there are 5 outcomes, so 5 out of 36. Plus my 2 even numbers, which we know there are 9 outcomes. But I have to subtract the events that are both a sum of 6 with 2 even numbers, which are 2 over 36. So these are not mutually exclusive events because they can both happen. So that ends up giving me 5 plus 9, which is 14, minus 2 is 12. So I get 12 out of 36, which ends up simplifying to be 1/3. So there's a 1/3 chance that if you roll 2 dice, you either can get a sum of 6 or 2 even numbers. So this leads us to our second formula, which is the general addition rule. So if A and B are any 2 events, then we can say the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. So the only difference between the general addition rule and the addition rule for mutually exclusive events is that when two events are mutually exclusive, the probability of A and B is 0. So then you end up subtracting 0. So the general addition rule can be used for any two probabilities, for if they're mutually exclusive or not, because if they're mutually exclusive, you don't end up subtracting anything. Now let's look at some examples with decks of cards. So this is, other than 2 dice, a deck of cards is probably the second most common type of probability that we're going to look at. So just kind of review, there are 52 cards in a deck. You have 4 suits. You have clubs, spades, hearts, and diamonds. And each of those suits have 13 cards, ranging from ace to king. So we have a lovely picture here in color. So my first probability I want to find is the probability I get a red or a queen. So half of my deck of cards is red cards. So I have 26 out of 52. Plus, each suit has a queen, so 4 out of 52. Now, if you notice, I can have red queens. So these are not mutually exclusive events, which means I need to subtract my 2 cards that are red queens. So 26 plus 4 is 30, minus 2 is 28 over 52, which does simplify to give us 7/13. Next, I want to find the probability of getting an ace or a king. So there are 4 aces, so 4 out of 52, plus there are also 4 kings, so 4 out of 52. Now, these are mutually exclusive events. I cannot pick a card that is both an ace and a king, so I don't have to subtract anything. So I get 8 out of 52, also able to simplify, and I get 2/13. The next one I want to look at is the probability of a queen or an even number. So we've already talked about the fact that there are 4 queens, so 4 out of 52, plus, now when I talk even numbers, 2, 4, 6, 8, and 10 are my even numbers. So every suit has 5 even numbers, 2, 4, 6, and 8, and 10. And there are 4 suits, so that means there are 20 even numbers. All right. A queen, not even or odd, so I don't have to worry about any overlap. So I get 24 out of 52, which simplifies to 6/13. I also want to look at, for my last example, the probability of getting black or an odd number. So if half the deck is red, half the deck is odd. So we get 26 out of 52 for our black. Plus, now this time when I look at odd, so 3, 5, 7, and 9 are all of my odds. 8 is not considered even or odd when we are talking about something like this. Ace is its own card. So each suit has 4 odd numbers, 3, 5, 7, and 9, which means there are 16 out of 52. Okay. Now, some of my odd numbers are black. So I do need to subtract my 8, because half of the odd numbers are black, so I do need to subtract 8. So 26 plus 16 minus 8 is 34 out of 52, which simplifies to 17 out of 26. For our next example, we have that students in an urban school were curious about how many children regularly eat breakfast. They conducted a survey asking, do you eat breakfast on a regular basis. All 595 students in the school responded to the survey, and then we have the resulting data in a two-way table. So they said they broke it down between male and female. So if we selected a random student from the school, we want to find the probability that they're female. So if I look, my column, here's my column of females. So there are a total of 275 female students over my total number of students in the school, which is 595. Which is approximately 0.46 as a probability. If you have fractions like this, like very large numerators and denominators, I'm not going to require you to simplify them. You can if you want, but you can also provide me with a decimal as long as that decimal is to at least 2 places. Second probability is someone who eats breakfast regularly. So if we look at our column, eats breakfast regularly, there are a total of 300 students out of the total 595 who eat breakfast regularly, which is approximately 0.50, about 50%. It's actually 0.504, so a little over 50%. Next, we want to look at a female and eats breakfast regularly. So if I look in my table, there are 110 female students who eat breakfast regularly. So that's going to be 110 over my 595. Which is approximately 0.18. And then lastly, a female or eats breakfast regularly. So this is a little bit different. So I want to find, so I already know the probability that you're female, 275 over 595. I know the probability that you eat breakfast regularly, 300 over 595. But as we've seen in the table, there is some overlap. There are females who eat breakfast regularly. So I have to subtract my 110 over 595. So 275 plus 300 minus 110 is 465 over 595. Which is approximately 0.78. So a lot higher probability than looking at them individually. Last example, we have hair and eye color of a group of women. Okay. So we've got the hair color black, brown, red, and blonde, and eye color brown, blue, hazel, and green. The one thing this table doesn't have are the totals. So I'm going to go ahead and calculate my totals for each row and column. So 36 plus 66 plus 16 plus 4. So there's a total of 122 with brown eyes. 9 plus 34 plus 7 plus 64 is 114 with blue eyes. There's 46 total with hazel and 31 with green. So then that tells me that if I add all of those numbers, I get the total number of people who were surveyed, which is 313. Now I'm going to do the same for my hair color. So 36 plus 9 plus 5 plus 2 gives me 52 with black hair. And there's 143 with brown. 37 with red, and 81 with blonde. And just to double check, those totals should also give me 313, which they do. So I know I have added correctly. Okay. So my first probability is going to be the probability that you select a woman who has red hair or green eyes. So I'm going to find my total number of red hair, which we know is 37 out of 313, plus my total number of green eyes, which is 31 over 313. And then I want to subtract my overlap. So my girls with red hair and green eyes, which is 7 over 313. Which is going to give us 61 over 313, which is about 0.19. Now we're going to look at red hair and green eyes, which we already found previously. Our red hair and green eyes is the 7 out of 313, which is approximately 0.02. Let me know if you have any questions regarding basic probability, whether that's mutually exclusive events, finding using the general addition rule for mutually exclusive events, or just the general addition rule, and then any probabilities using a table, dice, 2 dice, or a deck of cards.